Yeah. Hey, all, welcome back again. I am going to walk through examples 1, 2, and 4 from the notes we were just working on. You will notice when I flip over to my notes that I actually already filled in the tables for 1 and 2. We know that we are going to have to plug in all of the points all the way around the unit circle. And I am very confident that as long as your calculator's in radian mode, you will have no problem plugging in those theta values to produce the R values. So I went ahead again and I completed the tables for 1 and 2. Now, 3 we did together already. 4, I have not plugged the values in. You'll see my table, you'll see I have all the theta values listed. I haven't plugged them in yet, and there's a particular reason for that. So flip this thing over. Here we go. And we are going to start with 1. So while you look at my table, I am going to grab my book over here and I'm going to grab page 899 because although I have my table completed at this point, I could plot my points, but without being super familiar with polar graphs, I don't know what shape I'm expecting. So I am going to take this equation and I'm going to using page 899, which is again also posted on Canvas, I'm going to predict the shape that I am going to get. That'll help me connect the dots a whole lot easier. So I have 1 minus cosine theta. So the easiest one to just get rid of, I know that's not it. I'm sorry, showing you a book is really tough here. It's not a lemniscate. I don't have any of this R squared stuff. I'm going to throw that out. Circle. Now I see that I have this minus sign in here. Circles, well, they do have cosine in there, right there. I don't have any plus or minuses in circles, so I know that number 1's not a circle. Moving to our rose curves. Rose curves also do not have any plus or minus signs, which leaves me with the family of lemicons. This graph has to be in the lemicon family. I know that again because I have 1 is ultimately going to be my A. I have a minus sign, and this says I could have a plus or a minus. I have cosine, which would be this guy. Then what's my B? Well, keep in mind, we don't always have to write a coefficient of 1. It's really optional. So our B happens to be 1. We are in the lemicon family. And as I pointed out before, there's 4 different variations within the lemicon family. So knowing our A value and our B value, we should actually be able to predict further, and we should be able to predict which one of these lemicons we actually have. So to do that, we are going to look at the ratio of A to B. A over B, and every single one of them will determine which from the lemicon family we have. So our A over B is going to give us 1 over 1. Now notice that minus is not part of B. Notice it's plus or minus and just the coefficient in front is B. B has to be bigger than 0. It's a positive number, so is A. So 1 divided by 1 is obviously 1. So where does 1 fit in here? 1 is not greater than 2. 1 is not between 1 and 2. 1 is equal to 1, meaning the lemicon that we are going to have is a cardioid, which is also known as a heart shape. Cardioid, kind of like parabolas, we say are U-shape. A cardioid is this heart shape. So now knowing that we should expect this graph, it's going to make plotting and playing connect the dots a whole lot easier. So let's run through plotting those points. Okay, here we go. R value of 0, origin. Or excuse me, the pole. No longer called the origin, pole. Notice how tiny these R values are. We're not going to go very far out, but we're going to make it work. So at pi over 6, we are at 0.1, so I am barely out of there. I'm going to have to make it far enough that I can see it, but barely far. Pi over 4, we are at 0.3. Pi over 3, made it to a half. Pi over 2, we are all the way up at 1. 2 pi over 3, 1.5. 3 pi over 4, we are at 1.7. 5 pi over 6, we are at 1.9. Pi, we are at 1, 2. 7 pi over 6, 1.9. 5 pi over 4, 1.7. 4 pi over 3, 1.5. Probably starting to see that cardioid or heart shape starting to form here. See, we just did 4 pi over 3. 3 pi over 2, 1. 5 pi over 3, we are at a half. 7 pi over 4, 0.3. And 11 pi over 6, 0.1. Playing the connect the dots with this one probably would be very doable without having predicted, but predicting just makes it all that much easier to just verify, yes, we did this correct. And there we go. We have that heart shape or that cardioid. Well, notice compared to the book, it is facing the other direction. It's rotated 180 degrees. But remember, again, not all parabolas are the same. Not all square root functions are the same. So not all polar graphs are going to be the same. But we indeed got our lemicon cardioid. Now, I can see again that this is very symmetric. Symmetry with respect to theta equals pi over 2? No. This side does not look like this side. Symmetry with respect to the pole? No, I did not have any of that sliding going on. But symmetry with respect to the polar axis? Absolutely. Had I known that in advance, I could have just plugged in points or angles from quadrants 1 and 2 and flipped them over. But again, symmetry with respect to the polar axis. But again, unless you go on to watch these optional notes next week, you won't know how to predict that symmetry. So we can identify it after the fact, but we won't be able to identify it pre-graphing. Now, number 2, again, I went ahead and I pulled out I already filled in the graph, but let's talk about predicting what our graph shape happens to be. And I accidentally wrote it on here already, so I'm going to cover it up. We have something similar to last time. I definitely have a plus sign in here, which I'm going to leave my page 899 off to the side. You can go ahead and look at your page 899 or have it open on Canvas. Again, we can get rid of the lemniscates. There's no R-squareds. We can get rid of the circles because they don't have any pluses or minuses. We can get rid of the rose curve family, have no plus or minuses. We, again, are in the lemicon family. Now, I've already actually identified that this is a lemicon with an inner loop, and that is because we have an A value of 1 and a B value of 2. So when I look at that ratio, 1/2 is less than 1, which is what tells me we have a lemicon with an inner loop. That's going to make, again, playing connect the dots that much easier. So plotting the points, here we go. Angle of 0. We are 1 out at an angle of 0. Pi over 6, we are 1, 2 out. Pi over 4, we are 1, 2.4 out. Pi over 3, 1, 2.7 out. Pi over 2, we are 1, 2, 3 out. I don't know why I put a point there. I wish I had white out, but that definitely should not be there. We are at, 3 out. 2 pi over 3, we're at that 1, 2.7. 3 pi over 4, 1, 2.4. 5 pi over 6, 1, 2. Pi, we are 1 out. So far, so good. 7 pi over 6, we are at 0. Remember, R of 0, we're at the pole. 5 pi over 4, which would be right here, negative R value. So negative 0.4, positive 0.4 would be right here because here's 5 pi over 4, but we're going to slide back through the pole and we are going to go to negative 0.4, estimate to the best of my ability. 4 pi over 3, negative, so slide back through, 0.7. 3 pi over 2, oh, there's where that point came from. 3 pi over 2 would be right here, but negative 1, we're going to go back through. I guess we have that point after all. Don't know why I had it there previously. 5 pi over 3, negative 0.7, so we're going to go back through. 7 pi over 4, we're going to slide back through to 0.4. And 11 pi over 6, we are at 0. Now, this would probably be one that had I not seen the picture before, I'd be like, excuse me, how do I play connect the dots? Do I go in and out, in and out, in and out? Good practice also, if you're ever in question, is connect the dots in the order in which you plotted them. So if I keep that in mind, we went all the way around the outside and then moved back into that inner loop. Our lemicon with an inner loop. Now, we predicted because of the name in the equation, but don't forget, you can always type it into your calculator. I already have my equation typed in. I'm going to hit zoom 7 to make sure I'm in trig mode for the best viewing window. And yes, that looks very much like this. This one's a little compressed, if you will, but that's because this is not a square viewing screen. Okay, after the fact symmetry. Symmetry with respect to polar axis. No, this side does not look like this side. Symmetry with respect to the pole. No, I can't slide from here and get points down here. Symmetry with respect to theta equals pi over 2. Yes, these two sides are mirror images. Symmetry with respect to theta equals pi over the 2. For now, after the fact symmetry, watch those optional notes. I've said it before, and you will learn how to predict this ahead of time, so that way you don't have to plug in quite as many points. So, last one, we did 3 together. We are on to 4. Now, you've probably already guessed it. We've done 2 lemicons. We did a rose curve together in the notes. Circle we already did. This absolutely happens to be part of the lemniscate family, and the dead giveaway there is the R squared. So, a little bit more about the lemniscate family. We are going to identify more about this infinity symbol is really what a lemniscate happens to be. Lemniscates have this A value in here. All lemniscates have a 2. Notice a little bit different than the rose curves. The rose curves had n theta. Lemniscates are always going to be a coefficient of 2. Now, does that mean any theta that has a coefficient of 2 is a lemniscate? No. Rose curves can be a 2 theta. Lemniscates are always a 2 theta. So the only other special piece of a lemniscate is A, and we can tell by these pictures that similar to a rose curve, A is the length of a petal, if you will. I guess in some ways a lemniscate is a 2-petal rose curve. So we know that if our A, now what is our A? Is our A 4? Well, A is definitely located as the coefficient to sine. But sorry for this shaking of the camera. A, going back to the equation, this is actually A squared. This is actually A squared. Similar to having that R squared in front, this one is going to be an A squared. So what does A squared, what is A squared? Well, it's 4, which means A is actually 2 because A squared is 4. So that A means we have, if you can call it a petal again, a petal length of 2. Petal length of 2. Okay, so it's going to be if you want a lemniscate again, is like a 2-petaled rose curve, or it's an infinity symbol. We're going to have a length of 2. Again, I already identified all my special coordinates, but I wanted to talk through plugging these ones in together. So here we go. I can't do anything with the R squared right now, so I'm going to just type in 4 sine of 2 times theta, which is 0, and I get 0. Now, keep in mind, this is not R. This is R squared. So in order for me to come up with R, or what R is, I'm going to have to square root it. Well, a square root of 0 is 0. So now I'm going to do something similar with pi over 6. Pi over 6. And I get this guy. Again, keep in mind, this is not R, this is R squared. So I'm going to have to square root it to get my final answer of approximated as 1.9. Now, could I just put a square root around this entire input? Absolutely, I could do it that way as well. So continuing, I'm going to go with 4 sine of 2 times pi over 4. Square rooting my answer, because I know that's R squared. Square rooting my answer would give me 2. Plugging in pi over 3. I don't know the square root of that off the top of my head. I get 1.9 again. And going with pi over 2. Whoops, nope, I meant for pi over 2. 0, square root of 0 is 0. So first quadrant done, 3 more quadrants to go. If you want to pause me, feel free. Time for some 2 pi over 3. And, ooh, this is a weird one. Square root this guy, I get an imaginary number. Now, some of yours may say domain error. My calculator's turned on to give me imaginary. So if yours is that way, please make sure you pay attention to the end for that I. So let's talk about graphing imaginary numbers as polar coordinates. Or really, let's not. We are not going to. We cannot truly graph an imaginary point. So that just means a point doesn't exist for the angle 2 pi over 3. So now I'm going to go to 3 pi over 4. Ooh, I got a negative again. It might be a 4, but it's a negative 4. So when I go to square root that imaginary, I'm not going to have a point at 3 pi over 4. 5 pi over 6. Negative, again, go to square root it, not getting anything. Next, pi, and I don't want to get rid of my denominator similar to 4. So I'm going to do pi divided by 1. 0, square root of 0 is 0. 7 pi over 6. Is that 3.46? We had this one before. Square root is 1.9. Looks like I'm getting that same kind of similar values. 5 pi over 4. Square root of 4 is 2. And 4 pi over 3. And square root of that 3.46 again, 1.9. On to 3 pi over 2. And we have 0. Square root of 0 is 0. 5 pi over 3. It's negative. Square root it. I'm not going to get a real answer. Moving on, you can probably guess what's going to happen now, because since we're seeing a pattern, we can't square root negative 4. And last but not least, 11 pi over 6. And I can't square root a negative, no real point there. So I wanted to walk through lemniscates together because of that square rooting in those imaginary numbers. So again, we already know two-petaled rose curve. Lemniscate is an infinity symbol. We're going to have a length of 2. We'll notice we did not see anything over 2, so that's also a good sign. So let's get this one plotted. R value of 0, always at the pole. Pi over 6, we are at 1.9. Pi over 4, we are at 2. Pi over 3, we are at 1.9 again. Pi over 2, we are at 0. Now, again, you can play connect the dots in the order in which you plotted them. We're not done yet, but if you want to go that route as you plot, you can totally do that. But also knowing what to expect at the end helps play connect the dots tremendously. Nothing in the second quadrant because of all of these imaginary numbers. Pi, R value of 0. 7 pi over 6, 1.9. 5 pi over 4 at 1, 2. 4 pi over 3 at 1.9. So again, if I wanted to play and connect the dots in the order in which I plot, and I can see that lemniscate already. Isn't that beautiful? And again, in the fourth quadrant, all those imaginaries, we have our lemniscate. Now, this could very well be one of those where you would want to input a couple extra points just to know how wide this curve goes out here. So if I input a pi over, 15 degrees, pi over 12, and I input a 75 degrees, which is 5 pi over 12, we'll have an idea of how wide our curve needs to be. Now, again, this is optional at this point because we did this predicting. We knew how to play connect the dots. But if you just want this to be a little bit more accurate, then plugging in those extra angles could be really beneficial. So let's see, 5 pi over 12 is going to give me 2. And pi over 12 is going to give me, hey, look at that, 2. So at pi over 12, which would be right here, I'm actually 2 out. Now, let's see. Oh, wait, I have to square root those. Gosh me, I didn't square root those. Those are my R squareds. So let's square root a 2, and we should actually, See, Mrs. P messes up. We should actually be at 1.4. Don't forget to square root. So 1.4 would be about here. So really, if my graph was extra accurate, I should be a little bit wider. I think I was pretty good about the 1.4 at 75 degrees out here. And based on the symmetry, let's talk symmetry. I know I'm going to have similar width right down here, or the same width, really. So symmetry. Symmetry with respect to theta equals pi over 2. Nope, this side is not the same as this side. Symmetry with respect to the polar axis. No, top is not the same as the bottom. But symmetry with respect to the pole, absolutely. First quadrant and third quadrant are slides or reflections of one another. So we have symmetry with respect to the pole. Hopefully this helped. Again, there are some more equations that you can graph listed out in your book. Those particular problems are listed at the end of the notes, and they are listed, at the end of the notes, which is also on my PDF of the answer key. If you have questions, please let me know. I will talk to you later.